implementation of your processor device. That is, you implement the instruction set architecture by what's effectively a program in register transfer language, such as VHDL. And then you use tool sets that compile the VHDL down into a net list of transistor connections, and then you use other tools that lay that net list out onto a chip, and so on. From the RTL down, industry has pretty good verification tools to verify that the net list is functionally equivalent to the RTL and that the transistor layout correctly implements the net list. But they had very few tools for verifying that the RTL is a correct implementation of the instruction set architecture that you wanted. Because the RTL is like programming, and programs are hard to verify. So this Kami project is one way of filling exactly that gap between your desired observable behavior and the RTL. And it relies on the progress made in industry over the past 20 years in verification of the lower layers. The demonstration project for Kami will be a specification and verification of the RISC-V processor architecture. The first one will be a RISC-V implementation in FPGAs. This is basically done now. And our stretch goal is to have a high-performance implementation on silicon that comes from a COC-verified design. QuickCheck is a tool for specification-based random testing. It's based on the QuickCheck tool developed around 18 years ago or so by John Hughes and others at Chalmers University. And the idea is it's a kind of semantic fuzz testing of your program to suppose you haven't yet been able to prove your program correct, and you haven't yet even been able to write a full specification of it, but you can write partial specifications, and then you can do random testing to see in what ways your program violates those partial specifications. And in that way, you find bugs not only in your program, but in your specifications. So, and this all works in COC, where the specifications can be written in COC. The programs can be written in COC, but also the idea is to allow COC specifications of programs written in other languages. So that's QuickCheck, and in this summer school, early next week, we'll have lectures about QuickCheck, and you'll get to try this tool for yourself in the homeworks. In the DeepSpec project, we have several cryptographic verifications of not only cryptographic primitives actually, but cryptographic protocols. And these are going on both at Princeton and MIT. So there are various kinds of cryptographic verifications you might do, and I'll talk a little bit more about some of them later. But basically you want to verify that your programs correctly implement the functional specifications, and you might want to verify that the functional specifications give you the security properties you wanted, and both of those kinds of verifications can be done in COC. One project that's just getting started now, the DeepSpec database system, we aim to verify a high-performance concurrent main memory database system with a reasonably modern and sophisticated trie of B-trees with cursors that's sort of a mashup of recent work in Mastery project and SQLite. And we'll connect it to a query planner, that is a query compiler developed by some professors in Paris. So not too many results about that to report yet, but it should be great fun. In DeepSpec, we're also going to have an application demo. And for that, we're building a web server, the DeepSpec server. And this will run on a verified operating system. It'll be programmed in a language with a verified compiler, that is C. It'll have a verified file system We hope to have verified crypto in the TLS portion of it. So let me tell you about the DeepSpec web server. Right? What do you have in a web server? You have HTTP connected modularly to TLS, which connects to TCP, and a file system running on an operating system. And it's connected to the big bad internet. Now, because TLS has authentication, if somebody in the big bad internet sends you bad packets, you won't be too confused. But that also means that you don't need to formally verify the implementation of TCP. It might be a good idea, but if the TCP system sends you a message, then TLS checks the authentication on it and is not too confused. So at the moment, the focus is on verifying the HTTP server itself. There's other work done by parts of the DeepSpec team in verified file systems, and we hope to connect that in. There's other work ongoing in verifying components of TLS. And it'll run on the verified Certicos operating system. A web server is not only something you connect to over the internet that gives you static pages. Web servers are used as libraries in many kinds of applications now. When you install your Wi-Fi router, you connect up, the wired Ethernet and HTTP to a particular port to configure it. And therein, in the Internet of Things, lie all sorts of security bugs in the real world. So that having a lightweight, verified web server that's not just a static server but is a standard kind of library, web server library, could be useful in improving the security of the Internet of Things. And it would allow people to write applications that they can verify using the DeepSpec technologies and connect at specification interfaces to the web server. So in this summer school, towards the end of next week, we will have 2 lectures on the implementation and specification of the DeepSpec web server. And the web server serves as a demonstration for several of the DeepSpec technologies and sub-projects. But remember, DeepSpec is not just build a verified stack of applications. We really aim to build individual useful tools and individual useful scientific verification methods that are each useful by themselves and can be connected into in various ways for the task at hand. The DeepSpec server is just a demo. It's not the research. There's plenty of interesting research in it. So, DeepSpec is a coherent collection of tools and techniques that will allow you to connect, combine, and reconfigure to allow you to build and foundationally verify high-assurance, functionally correct software and hardware. So let me talk a little bit about the approach that many of us in DeepSpec take to verifying big chunks of software. When you do software engineering, you need to do it in a modular way, otherwise you'll never finish the project, and even if you manage to finish the project, you could never maintain it. And so when you do verification, you also need to do verification in a modular way. So here's a typical arrangement of a verification. We have a program written in C. We have a high-level property, something we want to verify about the observable behavior of this program. And instead of directly in one step verifying that the C program has the high-level property, we typically build a functional model of the C program. This might be a pure function in a functional programming language. Sometimes it's something else, like a state machine or whatever. And we do the verification in 2 layers, that the imperative program implements the functional model, and that the functional model has the high-level properties you want. And this allows, so this idea of functional programs as specifications is a kind of design pattern in verification. We in DeepSpec didn't invent it. We observe it used around the world in other interesting verifications. But it's a good pattern. And And by using the Coq proof assistant, whose logic contains a powerful functional programming language, we can use that language for writing down our functional models as executable functional programs. And so the advantage of doing this way is that the pure functional specification tends to be deterministic and total. And that means you get a kind of abstraction layer between the high-level proof and the low-level proof. That the functional model exhibits all the observable properties of the program, except the ones we define as not observable, like timing side channels. And it really does serve as a great abstraction boundary between these two levels of the proof. The other nice thing of the functional program as a specification is that in some cases, the functional program is the implementation. For those parts of your system where it will be sufficiently efficient and useful if it's programmed in a pure functional programming language with garbage collection, then you can just directly compile and run the functional program, and you don't even need the separate refinement proof down to an imperative program. So this two-layer method of verifying imperative programs also has the advantages of providing a kind of modularity of expertise. In my experience, in 2 or 3 of the verifications we've done this way, it's typically the case that the person that writes the functional model, perhaps by translating some English language document that describes, what the program is supposed to do, is one person. Then the requirements engineer who specifies the high-level property that this software is supposed to provide is someone else. Then we have the proof that the functional model implements the high-level property is done in the mathematics of your application domain. And so the application domain logician is the expert on that particular mathematics. If it's crypto, you have one kind of mathematics. If it's compilers, you have quite a different kind of mathematics. All right? That application domain logician may know not at all how to prove that a C program implements a functional model. It's not their concern. And meanwhile, the person that's doing the proof that the C program implements the functional model may not understand the mathematics of the application domain. They may not need to know why this functional program works. They just need to prove that the C program is a refinement of the functional program. So this modularity of expertise allows you to put together engineering teams, and not every C programmer will have to know how to do proofs in Coq. Okay, so here's then how you do program verification. Right? You write your language, your program, in a language with a nice proof theory, functional programming language. You use the program logic, Coq, to prove it's correct. You compile it, and you run your program. And most software, I think, should be written this way. It's only rarely that you need to write your software in a low-level language without garbage collection. There are some applications for which you need that. The implementation of a cryptographic primitive that does a certain kind of bit shuffling that A, needs to be really fast, and B, you need to be able to reason about the timing of it to avoid side channels. The implementation of some parts of your operating system kernel. The implementation of the runtime library of your nice functional programming language. There are several kinds of applications where low-level C programming or programming in other low-level imperative languages might be useful. And so these components of deep spec are related to that kind of imperative programming. But other parts of deep spec are useful in the model where you're just going to write functional programs and prove them correct, compile them, and run them. Okay, so I want to talk a little bit about verification of C programs. Here's a little C program that computes, the minimum of an array of integers. And here's a picture of a verification of it in progress in verifiable C. And up here we have the specification of the function written as a precondition and a postcondition in separation logic, a form of Hoare logic. Here is the theorem statement that the implementation of the program satisfies its specification. So F minimum is the abstract syntax tree of the program as parsed by the front end of the compiler, and min spec is the specification that's declared right here. And then this is a proof script in Coq that the C program function body satisfies its specification. We're at this point in the proof right now. So over on the right, as in any Coq verification, it shows the current proof goal, which is basically a Hoare triple, a precondition, a command, and a postcondition in separation logic. And here's a piece of the proof script that applies the proof rule for loops with this as the loop invariant. And so proving this kind of way, last year we published this kind of result, that the most widely used random number generator in the world, or rather the most widely used cryptographic random number generator in the world, is actually correct and secure. So a cryptographic random number generator is one that takes a short sequence of true random bits and produces a very long sequence of pseudo-random bits, such that the attacker who doesn't know the seed has an extremely small probability of being able to guess the next random bit that comes out. And so what did we prove? We proved that the embed TLS implementation of HMAC DRBG correctly implements the functional specification in the standard published by the National Institute of Standards and Technology. And we proved that that function, as published by NIST, correctly gives you the security property that an attacker with something like 2 to the 100 cycles of computation has a probability of guessing your next bit of only 50% plus 2 to the minus 70. Okay, so a concrete security bound. The upper proof is done in the computational monad of probability spaces, machine checked in Coq. That's the mathematics of the application domain. And the lower part of the verification is done using the verified software tool chain. And the undergraduate who did the upper verification in crypto, she has no idea how to prove C programs correct. And the undergraduate who did the lower verification of C programs has no idea how that probability stuff works. So this demonstrated the modularity of expertise. Okay. So let's talk about operating systems. What is a certified operating system kernel, right? What is its specification? And so here are all the properties proved in Coq for Certicos. Certicos is written in C. It's verified with this certified abstraction layers refinement technique in C with respect to the operational semantics of CompCert-C. And since the CompCert verified optimizing C compilers proved correct in Coq to correctly generate the right assembly code, then these are also properties of the assembly code. So functional correctness basically means that when a client of the operating system executes instructions, and those instructions, dereference memory, that the virtual page tables are set up so the instructions execute correctly. And when it does system calls, it gets the right behavior from the system calls. So that's a kind of functional correctness property. But then you want security properties, that the client in one guest partition can't read and write the memory or interfere with a client in another partition.